All right, so let's move on to question 2. And question 2 is we're given a series of measurements from, so we're trying to like do some weather modeling stuff, and we've got a set of measurements from some sort of like wind sensor, and we need to compute the average of all the data points that we're given. We don't know, well, I mean, we do know how many data points are, you can read it, but we should write our code to work for any number of data points. So we shouldn't just hard code how many data points there are. We also know that the data points will never be 0. So when we read a 0 at the end, that sort of indicates that that's all the data points that there are. So the data points are stored in a contiguous part of memory, that is, they're all next to each other in memory, and they're terminated by a 0 to indicate that that's the end of the data packet. So what we're going to do is we're going to write a piece of code that reads from this memory address and steps through, adding them all up. And we'll also have a register that keeps track of how many I've seen, and then we divide at the end. So we're also given in the question that the Ramesh supercomputer has been upgraded, so now we can use the multiply and divide instructions. So the first thing that we're going to do is we're going to use R0 as our counter for the memory address. So we'll load into R0 the address of measure. And so this will sort of point to where the data lives, and then we're going to use R1 as our counter. So we'll load 0 into it. That's our counter. And make that a comment. And we want the result to be in R1 afterwards. Alright, so here's the code for average. So what we do is we load from the memory address of R0. So we load from R0, and we'll store the result in, say, R2. So we use this command here to load something from memory. Well, we've got to be careful, because what this will do is it will go to the address of measure and read out 4 bytes. Now each of these data packets is a half word, because we're using the hword directive. So each of these little bits of information, each of these like packets of data from the sensor, take up exactly 2 bytes. So we want to use LDRH, which will load a half word from where R0 points and puts it into R2. And then we want to then check, have we loaded a 0, right? So we can check if we loaded a 0 by comparing R2 0. And if R0, then we want to compute the average. So we can branch to average finish, which will be another label that I'll deal with in a moment. And if we didn't load a 0, then there's more work to do. So we'll add the thing that I read from memory to R1. Sorry, R1's my counter, so I'm also going to need a register for the total so far. So maybe use R3 for the total. So we will add it to R3. We add 1 to R1. And then we want to increase R0 by 2 every time we do a load, because if I just load from where R0 points again, I'm going to fetch this bit of data. Thankfully, we can do all of this in one shot by using post increment. So if we have a look at our cheat sheet, load with post offset. So we're looking at this command here. So what this will do is it will go to where the RB register points, load that data from the address in RB into RD, and then afterwards, after it's on the load, RB will be incremented or decremented by the offset. So you should treat this command as go to R0, load a bit of data, go to where R0 points in memory, load data from that into R2, and then increment R0 afterwards by 2 bytes. Okay? So check if it's 0, branch if it's finished. Otherwise, we add this to the total, we add 1 to our counter, and we go to average and do it all over again. Alright? So R3 will contain the sum of all the bits of data, and R1 will contain how many data bits there were. And so afterwards, I want to divide, and because everything's all positive unsigned numbers, I'll do udiv. So take the thing in R3, divide it by R1, and store the result in R1. So again, we read like well, let's have a look at the cheat sheet, right? See which order it is. So if we have a look at division, take Rn, divide by Rm, store in Rd, which is indeed the order that we want. R3 divided by R1, store the result in R1, and then R1 should contain the average. Okay, so let's run it, see if it works. It's upset. And the reason it's upset is because I've tried to load a 0. These should be mobs. Oops, so that's a mob, and that's a mob. Alright, let's try that again. Alright, successfully built, that's good. Let's run it in the debugger, and we'll see what happens. Stick up. Oops. I probably want a breakpoint here. There we go. So rush through the code, get to my breakpoint. So we load the address of measure, which is OX 2000 whatever. Again, this is one of those times where hexadecimal is more appropriate. Yep, OX 2 million. We zero out the counter, and we zero out the total. Okay, so we load the first half word, which is 1358, into R2. We then check if it's 0, and it's not. We add it to the total, and again, having this in decimal will help us see what's going on a little bit better. There we go. We add 1 to the counter, we branch to average, we do it again. And you see how the R0 register has automatically incremented after running this command. So now we fetch the next bit of data, which hopefully should be 1853. Put it in R2. There we go. Is it 0? No, it isn't. So we add the result. We get this particular number here. We add 1 to our counter, and then we do it again. Again, our address is incremented by 2. You get the idea. So we're just going to let this run in a loop, and then we'll breakpoint here at udiv. So what's happened? Oh, I actually skipped that breakpoint. I should have put the breakpoint here, but that's okay. So what happened is that R3 contains the sum of all the numbers. If you sit here and add all these numbers up, you should get this quantity here. R1 did contain the count of all the things, and then we divided R3 by R1, store the results in R1. So the average of all these measurements is 1422, rounded down to the closest integer. Because it's probably unlikely if you sum all these things up and then divide by the number of things there were, you're going to get exactly a whole number. So naturally it will round down to the closest integer, and that's fine. We're working integer land, there's really no other way to handle that. So the average of all the data points is 1422.